Welcome back. This is going to be the last section of this workbook, of this course. This is what we're going to call 6.5, the binomial theorem. So this is going to make use of some of the stuff that we've done with combinations. It's not going to be very deep in its crossover with that. This ends up being fairly algebraic, but it's kind of pattern rich, and it shows us some stuff that ends up being a pretty useful algebraic tool. So it starts off with this idea about trying to expand a binomial. And we'll start with the simplest binomial, x plus y. And we want to evaluate this x plus y to the n for n values from 0 to 4. Well, the first couple of these are pretty trivial. Is x plus y to the 0 is just 1. X plus y to the 1 is just equal to x plus y. But what we want to kind of notice is it's 1x plus 1y. When we expand out x plus y squared, and we distribute this becomes 1x squared plus 2xy plus y squared. So these we know, and that's not that big a deal. We've seen all of that before. But if we're needing to expand out x plus y cubed, so there's a couple ways of looking at what's going on here. This ends up being x plus y times, we could write x plus y times x plus y times x plus y, but taking that, we know that our previous step is x plus y squared is x squared plus 2xy plus y squared. If I multiply that by x plus y again, that's going to give us the product of all three of these. And this ends up being, let's multiply x by each of those terms, is x cubed plus 2x squared y plus xy squared. Now we multiply y by each of those terms, it's going to be plus x squared y plus 2xy squared. And then our last term is plus y cubed. And I'm trying to conserve some room because we're going to have to do this to the 4 also. So just squishing this in here, this ends up being equal to x cubed plus, and then just getting like terms. This should have been 2x squared y. My x squared y terms, I have one of them here, I have 2 of them here. That gives me 3x squared y. My xy squared terms, I have one of them here, I have 2 more of them here, is also 3, but xy squared and then plus y cubed. So taking note of our coefficients, and so like I said, this is going to be 1x plus 1y, 1y squared plus 2xy plus 1y squared. And in this last one, we have 1x cubed plus 3x squared y plus 3xy squared plus 1y cubed. All right. So drawing the line and wanting to expand out x plus y to the 4. Now we could do this a couple of different ways. Of course, it starts off with the fact that it's just x plus y times x plus y times x plus y, or factors of this, right? And if I want to use what I just found in the cube, it's just going to be x plus y times x cubed plus 3x squared y plus 3xy squared plus y cubed. So let's use what we already have built here, and now let's just multiply this by x plus y. And if I do that, there's going to be one approach to organize our thoughts that is going to be helpful here. This ends up being x to the 4. If I'm multiplying this x by all of these, this ends up being x to the 4 plus 3x cubed y to the 1 plus 3x squared y squared. And then the last term is going to be plus 1x y cubed. Now to multiply the y by each of those terms, I'm actually going to write it underneath it, and I'm going to line up my like terms just to make it easier to multiply it out. y times x cubed is 1 x cubed y plus 3 x squared y squared plus 3 xy cubed, and then plus y to the 4. If I add this down, this gives me equal to x to the 4 plus 4 x cubed y plus 6 x squared y squared plus 4xy cubed plus y to the 4. Now, there's a lot that's going on in there. If we look at the values of our degrees of each of these terms, if we look at what's going on with our exponents, here we have x to the 4, and then x cubed, and then x2, and then x to the 1. And in fact, in this last term, we have x to the 0 because we have no factors of x. Anything 0 is just 1. So that's true. What's happening to our degree of y? Our degree of y is going up. So your degrees of x is going down by 1 each time. The degree of y is going up by 1 each time. The degree of each term is 4, right? So if you're summing the exponents of your variables, then each term is degree 4. And so we'd be able to put this together if we were asked for something like x plus y, maybe to the 8. We'd be able to start to put the variable part together pretty quick. But what is maybe tougher to see is these coefficients. So this is 1x to the 4, 4x cubed, 6x squared, plus 4x squared y squared, plus 4xy cubed, plus 1y to the 4. Okay, we'll get to that in a second here. So patterns that we should notice from this: when we had n was 0, we had one term. When n is equal to 1, when our exponent was 1, there were 2 terms. When our exponent was 2, there were 3 terms. And you can always kind of go back to those examples when we want to recognize what's going on with this pattern. When n is 3, there are 4 terms. When n is n, so whatever n is, there are going to be one more term than n. So we're going to say that there's n plus 1 terms here. So in each term, the sum of our exponents is, let's look at this x plus y squared, the sum of our exponents. In that was just 2. This was x to the 1, y to the 1. So the degree of that term is 2. The degree of this term is 2. In the cubic one, each of these degrees, the sum of the exponents, the variable's exponents, ends up being 3. And so the n is equal to the sum of the exponents. So 1, 2, 3, and n. This is essentially the degree of each term. For the most part so far in high school math, when we look at degree, we're just looking at the degree of a cubic polynomial or a quadratic polynomial, and it's just in x. But if we've got more than one variable, then we are looking at the degree of the whole term. So where we're getting to is this, is if we look at this pattern following here, this is called, this triangle here is called Pascal's triangle, named after French mathematician Blaise Pascal. What's going to be important in here is our first row. Once we start naming them, we would call it row 0, is n equals 0. So that's going to be important here in a second. Okay, so what Mr. Pascal noticed and started to do some work with is he says, okay, I've got this triangle of these hexagons. I'm going to start up at the top. I'm going to start with a 1. And every hexagon is just going to be sum of the 2 numbers above it. In this hexagon here, there's a 1 above it. And over here, there's nothing. So let's just call that a sum of 1 also. Now, we're just talking about the numbers that are directly above it, in the row above it. And so this just ends up being a 1. This just ends up being a 1. This is a 1 because we've got a 1 here. And this really is 0. There's nothing out there. So I add those together, and that's 1. But if I add these together, this is 2. And if I keep going with this process, then we have 1 down the sides on the edges. But 1 and 1, 1 and 2 is 3. 2 and 1 is 3. And this starts to fill in with some non-1 numbers. There's stuff other than 1 in here. We have this is 1, 4, 6, 4, and 1 when we're adding these together. Just adding the two numbers right above it. 1, 5, 10, 6 and 4 is 10, 4 and 1 is 5, and 1 here. So there's lots going on. If we look at all of these numbers down this row are all 1s, so are all these. But look at this row. And this is the numbers 1, 2, 3, 4, 5. There's some interesting patterns going on. If you look further in here, those numbers 1, 3, 6, 10 are called triangular numbers. And so there's ends up being some huge patterns with what's going on here. If you know stuff about Fibonacci, well, let's not get to that yet. If I look at the sum of the numbers in every row, this row adds to 1, this row adds to 2, this row adds to 4. 1 plus 3 plus 3 plus 1 makes this row is 8, this row is 16, this row is 32. Those are all your doubling numbers. And so there's tons of patterns going on with this. But for now, we're going to think of this as row 0, and row 1, and row 2, row 3, row 4, row 5. Now, where have you seen these numbers before? Well, this was what was going on with this. X plus y all to the 4 had these coefficients of 1, 4, 6, 4, and 1. Well, if we look back down at this, there is our coefficients in that row 4. And so if I wanted to expand out x plus y to the 8, for example, this would just be 1x to the 8 plus 8x to the 7, y to the 1 plus, and it's going to be some number of x to the 6, y squared. How tough would it be to find that number? Actually, not that tough. We would just go down to that row in Pascal's triangle. He noticed even more than that, though, because if we look at combinations, and if we use this is row 0, we could call this 0, choose 0. And because 0 factorial is defined, so is this. And 0C0 is 1. In row 1, I would look at 1C0 and 1C1. Now, these are all just 1, right? So it's not really that interesting thing. 2C0, I have 2 friends. How many ways can I choose 0 of them to take with me to the movies tonight? I have 2 friends. How many ways can I choose both of them? Well, those are each just 1. But 2C1 is I have 2 people. How many ways can I choose one of them? And that ends up being 2. And in fact, all of these numbers end up being exactly this. So we've now kind of come up with a formula for this. So this row will be 3C0, 3C1, 3C2, and 3C4 will give us all of these numbers here. 4C0, 4C1, 4C2, 4C3, 4C4. Now notice that these rows are symmetrical, front to back, left to right. There's one more thing that I have mentioned before in here, but I would like to mention again, is the symmetry of combinations. If I've got 5, choose 2. Here I've got 5, choose 2. Remember that our formula for 5C2 is going to be 5 factorial divided by 5 minus 2 is 3 factorial, and divide by 2 factorial. And that ends up being the same as this one, which is 5 factorial divided by 5 minus 3 is 2 factorial, 3 factorial. And those end up being the same because, well, just by looking at them, we're just multiplying the denominator, those 2 factorial and 3 factorial, in a different order. We're dividing by those in a different order. So this is called the symmetry of combination. It works out in that if you have 5 friends and you have to choose 3 of them to come out with you tonight, well, that's the same as choosing 2 of them to not come out with you tonight. And so that ends up being the same number of ways that way. A couple last things before we move to the next page is this. Another interpretation of what we're doing here is really we are finding how many ways can I take these x plus y's. And if I'm going to choose one from each, so think of each set of brackets as a basket. And we're going to either choose an x or we're going to choose a y. And then we're going to multiply them together. So how many, so from this first bracket, I'm either going to take an x or a y. The second bracket, so say I take an x and then a y, and then an x and then another x. Well, that would be x cubed y. How many ways would I be able to do that in total? Well, depending on what you're taking from what basket, there would be 4 ways of doing that. And so we could look at this binomial expansion kind of like that. One last thing that's really kind of interesting that's going on with this is this, and maybe you picked up on this when we did Blaise Pascal's triangle down here, and maybe you missed this. But when we saw this before when we were doing pathways. When we looked at pathways, we were looking at something like this. I'm at my house right now at A. I've got to get to my friend's house at B. How many ways can I get there if I'm only moving closer to B? And we started to remember that we started to count out how many ways you could get to each intersection. And if I'm at this intersection, I could only have gotten there one way. If I'm at this intersection, I could only have gotten there one way just by going straight east. Same thing down here. But as soon as I have some choices of how I could have gotten there, it's just going to be a sum of the 2 ways we could get there. If I'm on this corner here, where this 2 is, I've either come here this way or this way. And so there's 2 ways I can get there. Therefore, there's 3 ways of getting here. So this is just Pascal's triangle tilted 45 degrees. This row would be 1, 3, 6. This last number here is going to be 4. This is going to be a 6 plus 4 is 10. 1 plus 3 is 4. 6 plus 4 is 10. And 10 plus 10 is 20. Now, these numbers here, that's your Pascal's triangle. 1, 3, 3, 1, 1, 4, 6, 4, 1. Because that's really, essentially, it was built like this, which also ties in why we could use this, why we could do this with combinations. We could do this with, I have to travel a total of 6 blocks. 3 of those are going to be south. 3 of those are going to be east. And so really, I'm just making a word S-S-E-E-S-E or something like that. How many different words can I make? Apparently 20. All right, so this is all kind of coming together and tying in a little bit to the previous stuff. But at this point, it's going to get pretty algebraic. So a little bit of heavy algebra going on now. If I have x plus y to the n, what this is telling us is if I want to expand this out, this would be n choose 0. So nc0 times x to the n. That's going to be my first term. Now nc0, whatever n is just 1. But we're going to put that in there because it works with the rest of this pattern. My next term is going to be nc1. And whatever n is, nc1 will be that number. 9 choose 1 is just 9. But what's happening with our exponents? What we have here is we have x to the n minus 1. It's going to go down by 1. Our y's are going to go up by 1. So now this is nc1, x to the n minus 1, y to the 1. My next term will be nc2. And this is where it gets interesting. because in C2, we're going to have to calculate this way instead of just knowing that it's just 1 is the first term, n is the second term. This third term is going to look a little different. And so what's my x? It's going to be n minus 2, 1 less than this one was. Y squared, 1 more than this one was. And this pattern is going to continue. So I'm going to go plus dot 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 plus, and I'm going to leave room for writing something else here. Underneath this, because I'm running out of room, I'm going to write the last term, and the last term is going to be n choose n. By the time we count up to the last term, there's going to be no factors of x, and there's going to be n factors of y. So that's going to be your last term. But before we get to that, we're going to have this somewhere in the middle term. We're going to call it the general term, and what it ends up being is it's n choose, or nc. I'm going to use this letter k. So nck, our exponent on x is n minus k, and my exponent on y is k. So what that is called the general term. So it's nck x to the n minus k, y to the k, and this is binomial theorem. So this just represents any term. Perhaps it's in the middle, perhaps it's somewhere near the end or the beginning, but we're going to be able to use this to algebraically solve this. Where n is equal to your power of your binomial, x is equal to your first term, and as we get deeper into this, it's not just going to be x, it's going to be some other stuff in there. So our first term of our binomial will be just this. So therefore, the y is your second term binomial. Our k ends up being 1 less than our term number. Less than our term number. Okay, so essentially k is starting at 0. K is what back here on this page we were counting when we had 5C0, 5C1, 5C2. K is just going up by 1 in each term. That's what k is representing, and it starts at 0. So k is 1 less than your term number. So i.e., in your third term, k would be equal to 2. So that's kind of what it means by calling it tk plus 1. Now, one last thing before we move on is to recognize is that this sometimes throws some of us off. The fact that my exponent on x is n minus k and my exponent on y is k, that's just kind of a mathematical way of saying that those two numbers together, they add to n, right? So if n is 9, if your exponent on x was 6, then your exponent on y would be 3. Your exponent on y was 8, your exponent on x would be 1. All right, so let's go through a few of these examples. Number of terms in the binomial expansion, a plus 2 to the b halves plus 2. Ugh, wow, there's a lot going on in there. But the number of terms, how many terms do we have? We have 11. Then what's our value of b? Well, if we go back to what we know that x plus y to the 1 is just x plus y. There's 2 terms. X plus y all squared, x squared plus 2xy plus y squared. We have 3 terms. Students often get this the wrong way around. They know that the term numbers and your number n, differ by 1, but you can't remember which way it is. If you think back to what's going on in here, that will help you. So therefore, if that is giving us 11 terms, therefore, the fact that we have 11 terms, therefore, n is equal to 1 less. N is equal to 10 will produce 11 terms, just like an n value of 2 produced 3 terms here. So if n is 10, therefore, b halves plus 2 will equal 10. I subtract 2 from both sides, and b is 16. Determine our 5th term in the expansion. So we are wanting T5. We're wanting to find our 5th term. That means that k is equal to 4, right? If our formula says tk plus 1, what else do we know about this? We know that n is equal to 8. We know that my first term, I'd like to use a capital X, and it's just going to be little x. That second term represented by capital Y, and you'll see why in a few minutes here. And then that's just lowercase y. So therefore, what do we have? You've been told for years, always start off with a formula. Here, this is where this is very important, that you start off with your formula. I think that writing your formula actually helps you make sense of what you're writing here. So what do we have here? We have nck, big X to the n minus k, big Y to the k. So that's our formula. Again, I'll get into this in a minute, what I mean by big X and big Y. And so what do we have here? K is 4, so this is T5. N is 8, so we have 8C. K is 4, so this is 8C4 is going to be our coefficient. We have X to the 8 minus 4, Y to the 4. This melts down quite nicely. 8C4, if we push that through your calculator, is 70, X to the 4, Y to the 4. So here's your 5th term. So we could just do this a bunch of times and write out your whole expansion. Number 3, determine the middle term. What do we have here? We have n is equal to 6. If n is 6, that means there are 7 terms. If we are wanting to find the middle term, if we have 7 terms, if we have an odd number of terms, then we are looking for T4. That would mean that k is 3 in the term that we're looking for. We're looking for the 4th term out of the 7 of them. So that's going to be our middle term. We have, now here's what I'm talking about with using capital X. X in our formula is this. So I'm going to call it 2x. We could have x's present both in the first and the second term in here. We could be using different letters altogether. So to differentiate this x from that x, I like to call that big X. Big Y ends up being, be careful, this is -5. That negative sign has to follow that. Plus -5. And that's all we have. That should be enough for us to figure this out. Let's see what we have. TK plus 1 is equal to CK X to the n minus k, Y to the k. We are looking for T4, so therefore k is 3. We have 6C3. Now we're going to replace big X with 2x, and we have, and our exponent on this ends up being 6 minus 3. Our y value is -5, we put in brackets, and our exponent will be 3. And it should all just fall out quite nicely. 6c3 is 20. We have an exponent of 3, so this is times 2 to the 3 times x to the 3 if we're distributing, and then times negative 125. If I multiply all that out, 2 cubed is 8. 8 times 125 is 1,000. So we have negative 20,000 x to the 3. 4. All right, number 4. Given 5x minus 2y is equal to 9, determine the coefficient containing x to the 5. Okay, so we know that n is 9. K, we don't know. We're going to have to figure out what k, we don't know what term number it is, so we're going to have to figure that out. Front term is 5x. Back term is negative 2y. And let's see what happens. If we start with our formula, tk plus 1 is equal to n ck. X to the n minus k, y to the k. N is 9, so this is 9ck. We're going to leave it at that. X is now 5x. Our exponent is 9 minus k. That's the best we can do with that. Y is negative 2y. And our exponent on that is k. That's all that we know. Now, a couple things about this. We should keep in mind that n minus k and k, those just add to 9. They're just two numbers that add up to 9. We also have, we should maybe start to separate this into a numerical part and a variable part. So I have 9ck. That's just going to be a number. Whenever we figure out what k is, that's just going to be a number part. We have this times 5 to the 9 minus k. That's also just going to be a number, of course, once we figure out what k is. And then negative 2 to the k. This part here is all numerical. And then it's multiplying by x to the 9 minus k times y to the k. This part is variable. Now I'm going to switch pen colors here because this is going to be a bit of an aside. And so we're going to make the argument that x to the 9 minus k has to be equal to x to the 5. So we're told in the question, we're trying to find the x to the 5 term. There's no x's going on in this y. And later on, we're going to see questions that combine those. So really, we have x to the 9 minus k is equal to x to the 5, which implies that therefore 9 minus k equals 5. And that tells us that k equals. Now I'm doing this in a different color, and I'm doing this horizontally because this is kind of just an aside to our argument. I'm going to continue on with this, equals tk plus 1. But now it's t4 plus 1. And it's now equal to, well, let's start filling in k. So 9c4 times 5 to the 9 minus 4 is 5 to the 5. Negative 2 to the 4, that's all of our numerical part. Our variables is now 9 to the x to the 9 minus 4 is x to the 5, y to the 4. If I simplify this out, 9c4, you chuck that in your calculator, 126. 5 to the 5 is 3,125, and negative 2 to the 4 is 16. We're multiplying all these, x to the 5, y to the 4. After everything is said and done, this is T5 equals 6,300,000 x to the 5, y to the 4. Now, this question kicks it up a notch in a couple of different ways. One way is both our x and y terms now have the variable x in them. That's not going to matter if we just kind of treat this the same as we did in the last ones. If we look at this, this is 3x cubed. We're multiplying this 6 factors of this binomial together. Our first term, you could probably guess, would be 3 to the 6 times x to the 18. And then there's going to be a bunch of terms in the middle. And then my last term is going to be 1 over x to the 18. Or in other words, x to the negative 18. Well, somewhere in the middle here, we're going to have a term. Somewhere in the middle here, we're going to have a term that is x to the 0. That's what this means by constant term. And it's going to have some sort of coefficient on it. That's essentially what we're going to be left with. So when it asks for a constant term, that's asking for your x to the 0 term. We know that n is 6. We know that k is unknown at this point. Our big X is 3x cubed, and our big Y is x to the negative 3. So our formula is tk plus 1, nck, x to the n minus k, y to the k. Always keep in mind when you're writing that formula that x is really big X here, right? We don't know what k is yet, so let's still call this tk plus 1. We have 6ck. Big X is 3x cubed to the 6 minus k. Our big Y is x to the negative 3 to the k. If we try to separate numerical versus variable, 6ck is just going to be a number. 3 to the 6 minus k is just going to be a number. And we don't have a coefficient on our y term, so we'll just leave that out. If it was subtracting here, then that would be -1 would be the numerical part, right? So be careful about that. But our variable part, so there's all of our numbers. Our variable part ends up being x cubed to the 6 minus k. So this is x to the 18 minus 3k times x to the negative 3k. And we can simplify those and multiply them together. So 6ck, 3 to the 6 minus k still. And then our variable part is 18, adding these because we're multiplying these powers together. So 18 minus 6k. Here's now where we are going to do our aside. And say, what, 18 x to the 18 minus 6k is equal to x to 0 because we're wanting our constant term. That implies that 18 minus 6k equals 0, which implies that k equals 3. So now we can go back to our k is equal to 3. So this is now T4 that we're trying to find. 6c3 times 3 cubed times x to the 18 minus 6 times 3. 6c3 is 20. It's 27. X to the 0. Therefore, T4 is equal to 540. 6. Determine the expansion of x plus b to the 7 is 21,504, x to the 5, y to the 4. So tk plus 1 is not equal to question mark, it's equal to 21,504 x to the 5 over y to the 4. We don't know what k is, what term number it is, but we know it's in there somewhere. And we know that big X is just X, and big Y is this unknown B. Should state one more thing about this. I suppose if we don't know if there's any X's in that B, then I suppose we wouldn't be able to do this question. But if we assume that there's no X's in there, now we can get this done. So let's start off with our formula, tk plus 1, ck, x to the n minus k, y to the k. So on the left side, I actually have 21,504 to the 5. On the right side, we have 7ck. X is just X now, 7 minus k. And Y is equal to this unknown B. That's what we're going to try to find, B to the k. And one more time, we'll go through this and we'll say x to the 7 minus k equal to x to the 5. Because we know that it's going to be exponent 5, therefore 2. Jump back in here. We have 21,504 to the 5 over y to the 4 is equal to 7c2. X to the 7 minus 2 is x to the 5, and this is b squared. Some of this will simplify out right now. We divide both sides by x to the 5. Leaves us with 21,504 over y to the 4 is equal to 21 is 7c2, b squared. Divide both sides by 21. Now we have b squared is equal to 1,024 over y to the 4. Square root both sides. B is equal to the square root of 1,024 over y to the 4. Don't forget the plus minus on this because we are taking an even root. We're taking a square root. And we're almost done with this. Therefore, b is equal to plus or minus square root of 1,024 is 32 over y squared. Or we could call it 32 y to the negative 2. And so for our last one of this workbook and the last one of the course, given 8x to the 6 minus 7y cubed to the 9, determine the position of your x to the 36 term, and then determine that term. So n is equal to 9, k we don't know, big X is 8x to the 6, big Y is negative 7y cubed. Formula 2k plus 1 is equal to nck, x to the n minus k, y to k. This will be equal to 9ck, 8x to the 6, all to the 9 minus k, negative 7y cubed, all to the k. So again, let's try to separate our numerical part and our variable part. The numerical part includes 9ck. It includes 8 to the 9 minus k. It includes -7 to the k, and all of that is this number. The variable part is going to be x to the 6 to the 9 minus k is x to the 54 minus 6k. And then for our y, we have y to the 3k. But our side says x to the 54 minus 6k is 36. Therefore, 54 minus 6k equals 36. -6k is equal to -18. Therefore, k is equal to 3. We could also do our side like this. Just clearly mark it that it's not part of the same logical thought process as our tk plus 1 line was. Now we know that k is 3, therefore this is t 3 plus 1 is going to equal 9c3. 8 to the 9 minus 3, -7 cubed times x to the 4 minus 6 times 3, y 3 times 3. Filling all this in, this is 84. 8 to the 6 is 262,144. -7 cubed is -343. And then what do we have for x? This is x to the 36, y to the 9. This is T4. So T4 is equal to, when we multiply that all together, we get -7,552,892,928 x to the 36, y to the 9. That is it. As always, if you have any questions, please ask. And good luck.